Are you ready to go, Vasco?
Yes, I'm ready to start.
Okay, so we're running 5 minutes late, so please feel free to take 5 minutes past the hour. All right, I'm very pleased to introduce Vasco Brattka, who will speak on which Weihrauch degrees correspond to logical axioms.
Yeah, many thanks for the introduction and many thanks for inviting me to this nice meeting. I really regret that I can't be there in person, so sorry about that. So today I'm not talking about my most recent research results, but it's more like a survey or programmatic talk. So I will raise this question, which Weihrauch degrees correspond to logical axioms, and I will kind of review the question in light of several research results of other people. So first I will recall some basic stuff from on Weihrauch complexity. Then I will tell you a little bit about constructive reverse mathematics, and then I will go on with certain worlds of classical reverse mathematics. So basically, my question is about such pictures. So we often present such pictures where you can see certain Weihrauch degrees. Don't worry too much what they are. I will tell you a little bit about that later. And then we are saying, okay, these degrees, they correspond to certain axiom systems in reverse mathematics. And of course, it's debatable whether these associations are appropriate. So my question is, are these correspondences really justified, and how can we actually evaluate or measure that? Are there necessary requirements that a Weihrauch degree needs to satisfy in order to be a candidate for such a correspondence? And if you have distinct Weihrauch degrees which somehow correspond to different theorems that are equivalent, say in reverse mathematics, which of these Weihrauch degrees is the legitimate representative, and are there any criteria for this? So what do I mean by classical reverse mathematics? By classical reverse mathematics, I just mean reverse mathematics as you all probably know it in the sense of Friedman and Simpson. So that is second order arithmetic, and we measure theorems according to which axiom systems are required to prove them, and in the ideal case, they are equivalent to such a system. So some of the most discussed systems are WKL naught, ACA naught, ATR naught, and we'll come to those later. So in case of constructive reverse mathematics, there are also many different kinds of schools or formalizations, how you can do that. So if I'm talking about constructive reverse mathematics, I rather refer to the informal type of reverse mathematics in the sense of Ishihara. So there you classify theorems in intuitionistic logic according to certain non-constructive principles such as LPO, LLPO, and so forth. So classical reverse mathematics is built on classical logic, constructive reverse mathematics is built on intuitionistic logic. And then there are some other notable differences. For instance, in this informal world of constructive mathematics, you allow the countable axiom of choice, but not Markov's principle. So this generates some differences. Okay, so let us talk about bioreducibility. We have heard a lot about this notion also in the previous talk, so I'm not going to say too much. But the intuition is basically that F is bioreducible to G if we can use one application of G to compute F. So that's the intuitive way to think about this for this talk. We know that we get a distributive lattice in this way with some supremum and infimum operation. So here are some of the most common binary operations that we consider in this lattice. So we can put problems into parallel. So that means we have instances for both, we get solutions for both. Then we also have this compositional product. We also have heard about that. So I don't want to give you the exact definition. I think the best way to think about it is that this is the most complicated thing that you can do. If you first apply G, then you do some computation, and then you apply F. So both have to be used exactly once, but in this particular order. Okay, then what is the supremum in our lattice? So the supremum is the coproduct. So we can use both problems F and G, but we have to decide which one. So we can either give an instance for F or an instance for G, and then we get the corresponding answer. But we cannot evaluate them in parallel. The infimum in the lattice, that's just defined like this. So we give two instances, one instance X for F, one instance Z for G, and we only get one answer. So either the answer for F or the answer for G, but the problem tells us which of these two answers, which of these two questions is actually answered. So there is a bit, so to say, that tells us it's the answer for the first one or for the second one, for F or for G. And this is kind of an OR operation. It's kind of a constructive version of an OR operation. And we have a second version of an OR operation that I call plus here. And here we are also given two instances, one for F and one for G. And we get back a pair where one component is actually a correct solution and the other component is a dummy solution, which is completely arbitrary. But we are not told which one is the correct one and which one is the dummy solution. So one has to be correct, but we don't know which one it is. And in order to make this possible, we need the completions of these spaces. So that's what this bar stands for. I don't want to go into the technical details here, but that's how we can define a more classical sort of an OR operation in our lattice. And actually these two OR operations, they kind of correspond to the additive and multiplicative OR from linear logic. So the supremum and the parallel product likewise correspond to additive and multiplicative ends in linear logic. So then we also have a couple of unary operations in the lattice structure. So star is just the finite periodization. It's like a Kleene star. So we can ask a finite number of questions to F in parallel, but we have to say how many. So the parameter n is part of the instance. We have to say how many questions we want to have answered in advance. In case of the parallelization, we get a whole sequence of instances and the whole sequence of solutions in parallel back. So it's like a countable product of F with itself. And then we also have this more recently defined operation F diamond, which is kind of a closure under compositional product. So by results of Linda, we know that we can actually characterize this F diamond such that it's the minimal Weihrauch degree above F, which is closed under the compositional product. Now, it's not evident that such minima and maxima exist in the Weihrauch lattice. The lattice is not complete. So this always requires a proof that such a minimum actually exists. And we also have a completion operation, which you can think of as the simplest way of converting F into a total problem. So our problems F, they are allowed to be partial, but sometimes we want to work with a total version of it. And if we use these completions of the input and the output space, then we can convert F into a total problem, which we call the completion here. So all these operators that we have, the first four, they are all closure operators. So that means if you apply them twice, you don't get any mu. So it just remains stable and it's monotone on Weihrauch degrees, so and reflexive. So it's what is called a closure operator. The other two guys here, they are obviously not closure operators. The first one is what we call the jump in the Weihrauch lattice. It's roughly, if you think about bare space problems, it's roughly as if you compose your problem with a limit operation. So instead of having an input X, you only get a sequence that converges to such an X. And then finally, I want to mention the ordinal iteration that was defined by Arno. So that is an iteration along a countable ordinal. I don't define this precisely here, but roughly speaking, it means that in the successor cases, you do a composition with F, and in the case of limit ordinals, you do a parallelization. Okay, now I want to tell you this thesis. It's not really a theorem because there are some vague terms in it, but I will try to make that more precise in the course of my talk. So I'm claiming that a Weihrauch degree corresponds to an axiom system in some formal system of reverse mathematics if it's Weihrauch equivalent to the compositional closure of this little t, which is the interpretation of a theorem that is equivalent to those axioms in that formal system. And I'm saying here it has to be a suitably strong interpretation. Of course, this is a vague term. There is no clear meaning to that, but I will tell you a little bit more about what I mean by this. Okay, now how do we interpret theorems in our lattice? So the standard interpretation. So the standard interpretation is that we have a for all exists theorem of this logical form for all x that satisfies some requirement. There exists a y with some property. And then we translate that into a Weihrauch degree from x to y. So this x is considered as instance, this y is considered as solution. The solutions have to satisfy the property, but the domain is restricted to those instances which actually satisfy this extra requirement. So this extra requirement is kind of something non-constructive. It's just a promise. All our inputs satisfy these requirements, and we only want to solve the problem for those particular instances. Sometimes it's not so straightforward. I mean, not all theorems have such a for all exist form. And so it's not so straightforward to see what the corresponding interpretation is. And we will come back to that in case of some examples. Now, why am I demanding closure under composition here? So the reason is that this roughly corresponds to closure under deduction. And that's something that we have kind of for free in the logical theory, but we don't have it for free in the Weihrauch lattice. So that's why I think that it's reasonable to ask that our theorems that are our degrees, which are such representatives, axioms, they should be closed under composition. And if we go to other worlds of reverse mathematics, like in the constructive case where we have countable choice, we should even add further closure principles such as parallelization. Okay, so here's basically a picture which explains what I have in mind here. So if you have some formal system in the usual logical sense, then you have this cone here, which is kind of the theory of your theorem. So that's everything that you can deduce from your theory. And the idea is that this should kind of correspond to the lower cone of the correspondent of that theorem in the Weihrauch lattice. So the lower cone should kind of should reflect this theory of that theorem. But in logic, we have a closure under deduction. So if we can use S from T and R from S together with T, then you can also directly deduce R from T. And if you translate that to the Weihrauch world, then this just means closure under composition. And if you have countable choice, then you should also have closure under parallelization. And there are other issues. If you work with classical logic, such as in classical reverse mathematics, then you have contrapositive forms of certain theorems which are equivalent to the original theorem in classical logic. And so in such a case, we should take the more complicated one of these two. because otherwise this picture is no longer correct. So you have to think about it like that. If you, in your formal system, you can do something with your theorem, then you should be able to do the same thing here with your cone. And that requires that this cone, this problem that defines this cone has certain closure properties. So if your contrapositive form of the theorem is more complicated, but still in the theory, it should not jump out of the cone here. And so that's why we need requirements as these ones. Okay, now the most important problem in Weihrauch lattice is perhaps the choice problem. You can think about it like that. Perhaps that's the most intuitive way. You have a function from some space X to the real numbers, and the problem at hand is to find a zero of this function. You can imagine that a lot of problems in mathematics can be seen as problems that where you want to solve an equation with a continuous function, and whenever that is the case, then you have such a choice problem that is related to it. And the point is that depending on what the space X is, this choice problem is more or less complicated. So we usually express that in a different way. We are saying the choice problem takes as an input a set, and the goal is to find a point in the set, but that's equivalent for, at least for computable metric spaces, because you can think of this zero set of a continuous function as a negative representation of a closed set. And so in that sense, these two things are equivalent. But I don't need to explain to you what the space is, because here we have the explanation in terms of continuous functions. Okay, then we also have variants of these choice problems. So for instance, UCX stands for the unique choice problem. So it's the problem of solving such an equation that has a unique solution. And there is also positive choice, which is about such equations where the set of solutions has positive measure. Of course, this requires that your space is compact with some measure. Then we also have compact choice, where we have more information about the input. So the input is a compact set, not just a closed set. And the additional information is that we have some kind of bound on the set. And then we also look at total variations of choice, which are defined such that for an empty set, you can choose anything, and otherwise it's the same as before. Okay, let me skip these slides, come back to this picture here, which I already showed you initially. So you can see that a lot of these problems here are choice problems. Choice on bare space, unique choice on bare space. Then here the parallelization of choice on the natural numbers, choice on the reals, positive choice on the reals, and so forth. So a lot of choice problems occur actually as correspondence of certain axiom systems. Now let's look at some specific example. So my first example comes from constructive reverse mathematics. So here the basic principles or the basic systems that people look at are LPO and LLPO. So they have been defined by Bishop as far as I know. And LPO stands for the limited principle of omniscience, and LLPO for the lesser limited principle of omniscience. So this sounds mysterious, but it's a pretty simple thing. So LPO is just the zero test. It tests whether a sequence and point from bare space is the constant zero sequence or not. So in that sense, it's kind of the principle of excluded middle for such sigma 0,1 predicates. And likewise, LLPO can be seen as De Morgan's law for such predicates. Here we get as an input a pair which is altogether different from the zero sequence. So one of the components of this pair must be different. And the point is to find one which is different. So it's kind of a realization of De Morgan's law. Likewise, LPO is a realization of excluded. These two principles are considered as non-constructive, and a lot of things in constructive mathematics are either equivalent to LPO or to LLPO. So we can also see LLPO as a choice problem. It's equivalent to choice on the two-point space. The periodization of LPO is the limit on bare space, so the limit operation on bare space, just in the usual sense. And the periodization of LPO is weak-Koenig's lemma, which in turn is equivalent to choice on Cantor space. Now, if you look into results in constructive reverse mathematics, you see theorems like this one. LPO is equivalent to the Bolzano-Weierstrass theorem. And it's a bit surprising on the first side, but if you look into the proof, then you actually find what they do is they parallelize LPO and take it in a compositional product. And that's then strong enough to get the Bolzano-Weierstrass theorem. If we interpret the Bolzano-Weierstrass theorem in Weihrauch complexity, it's just this problem given a sequence of real numbers, which is bounded. That's the promise. And the goal is to find a cluster point of that sequence. And we can kind of state a finer characterization, namely the Bolzano-Weierstrass theorem, the jump of weak Koenig's lemma. Okay, but now we get a problem here, because if we want to understand what's the Weihrauch counterpart of LPO or LLPO in constructive mathematics, we kind of need something like this here. So the smallest problem above F, which is closed under composition and parallelization simultaneously. And this operator has not been studied, so this is kind of a problem. I would like to see a study of this one. So for which F does it actually exist? What kind of properties does it have? How is it related to the dagger operation that Arno considered? So for instance, I think it's easy to see that if a problem F is simultaneously closed under composition and parallelization, it's a fixed point of the dagger operator. The dagger operator is not a closure operator, so you have to be careful when using it. Arno noticed that it's not a closure operator, so it can happen that F dagger is not itself closed under dagger. But if you have a fixed point of it, then it's the same as a problem that is closed simultaneously under composition and parallelization. Okay, so there are lots of interesting questions here, and I will illustrate them with some examples here. So it's known by results of Arno and Eike Neumann that the compositional closure of LPO is choice on the natural numbers. And by recent results of Giovanni Solda and Manlio Valenti, that the compositional closure of LLPO is compact choice on the natural number. Arno also proved that LPO dagger is unique choice. Oh, here's a typo. This is meant to be a bare space. Sorry about that. So it's unique choice on bare space. Okay, now if you look at these examples, so what happens if you start with LPO and you take a closure under composition, you get Cn. If you parallelize that, you get the limit on bare space. If you take the closure under composition, you get something larger again. If you take the periodization, you get again something larger. And it seems that kind of the stabilization of all that is then a unit choice on bare space, which is the dagger of LPO. And so here, in this case, taking repeatedly closures under composition and parallelization leads to a long chain. Question, how does it look exactly here? In between, so how can we know that this is here all strict? For instance, you can easily see that the periodization of the compositional closure of limit allows you to define something or compute something as the omega jump operator. So here is the step from arithmetic results to arithmetic results, so to say. And so this is really getting more complicated. So if you want to have a simultaneous closure under composition and parallelization, it's not enough to take one closure and the other after each other, no matter which order. It will not be enough to get a simultaneous closure. So you need to climb up along an ordinal, possibly here. In case of LLPO, the picture looks much simpler. So if you take the closure under composition, you get compact choice on the natural numbers, which parallelizes to WKL. And that's where the whole chain ends, because WKL is closed under composition and parallelization. So here's a very vague correspondence. I know that this is not quite appropriate, but we could roughly say that LPO as a constructive principle is somehow related to the dagger of LPO, and likewise LLPO is related to the dagger of LLPO. So the second case, there we have a proper coincidence. In the first case, this is a bit debatable. So, for instance, would that really be acceptable to say in constructive mathematics that LPO proves the existence of the omega jump operator? So I don't know what a constructivist would say. You would have to use LPO repeatedly. You would have to use the axiom of countable choice, use that result again repeatedly, and use the axiom of countable choice again. So that's pretty strong. I'm not sure whether that would actually be admissible here. Okay, now let's move away from constructive reverse mathematics. This was just meant to show that there are interesting questions that one can raise here. Now let's look at classical reverse mathematics, and in particular induction and boundedness principles. So I've already given you the definition of closed and compact choice, but in case of the natural numbers, you can characterize that more easily. So choice on the natural numbers basically means give me a list P of numbers and find one number which does not appear in the list. And the promise here is that there is at least one such one. The difference of compact choice is now that you get the sequence together with an upper bound. And the goal is to find a number which this promise the entire sequence is.
Hey, Vasco, we lost you for a minute. Could you just start that sentence again?
Okay, did you follow what I said in closed choice?
Let's just start from there.
Okay.
Thank you.
So I'm saying I gave you a definition of a closed choice and compact choice in the general form, but for natural numbers, this is much easier to characterize. So closed choice on the natural numbers essentially means give me a list of natural numbers, and I want to find a number which is not in the list. And the promise is there is at least one such number. So the list does not exhaust all natural numbers. And likewise, compact choice on the natural numbers means that we have the list together with some upper bound. We want to find a number which is not in the list, obviously below the bound. And the promise is that the entire list stays within that bound, but does not exhaust all numbers 0 to n. Now, as I mentioned before, it's known that the compositional closure of LPO is this Cn, and the compositional closure of LPO is this Kn. So these are relatively recent results. Now, how do you characterize, or how do you use sigma 0,1 induction in reverse mathematics? So you often use that in the least number principle, which we can translate into a Weihrauch problem. It's just the infimum. So it's the same task, so to say, as choice on the natural numbers, but we want to find the minimal number which is missing in the list. And likewise, I already mentioned the Bolzano-Weierstrass theorem on the reals. You can also define it on natural numbers. And there it's the problem of finding a cluster point in a given sequence, which is promised to be bounded. Now, it's very easy to see that choice on the natural numbers is equivalent to the least number principle. And we have proved that choice on compact choice on the natural numbers, when you take the jump of it, gives you the Bolzano-Weierstrass theorem on natural numbers. And one can also see that these problems, if you take jumps, so this n in brackets stands for the nth jump. So if you take jumps, then they are kind of linearly ordered in this given way. So compact choice is below closed choice, and the compact choice with jump one level higher is above closed choice in that level. Now, as I mentioned, so in reverse mathematics, the least number principle is seen as an equivalent formulation of I sigma 0, 1 induction. And the Bolzano-Weierstrass theorem, sometimes called the regularity principle there, is seen to be equivalent to B sigma 0, 2, so the boundedness principle, sigma 0, 2 boundedness principle. These equivalences, which are mentioned here, they hold over a very weak base series, so it's included in this book of Ajek and Putluck. This led us to the conclusion that, well, this linear order of principles here in the Weihrauch lattice is really corresponds to this linear order in reverse mathematics. So I think it has been proved that this is a strict implication chain, and likewise we have a strict chain here in the Weihrauch lattice. But the question now is that really justified that to say that these principles, these Weihrauch principles here, are correspondence of these logical principles? All we know is that we have one thing, the least number principle, which is equivalent to choice on the natural numbers, and in reverse mathematics it's equivalent to this one. And we have one principle here in reverse mathematics that is equivalent to the Bolzano-Weierstrass theorem, which is equivalent to Kn jump. So we have this correspondence here. But is this mere fact that we have a theorem that is equivalent already enough to say that these are correspondence here? And my answer is no, this is not enough, because if we want to have closure under deduction, then we need closure under composition. But fortunately, this was recently proved. So for the jumps of choice on the natural numbers, this is already known for some time, but this is unpublished. It was proved by Solder and Valenti independently. I didn't find the second claim in their work, but I was able to deduce this easily using their methods. So fortunately, we have closure under composition here. And only because this additional feature is given, I think it's appropriate to say that these principles are the compact jumps of compact choice on the natural numbers. They are the correspondence of the boundedness principles, and the jumps of choice on the natural numbers, they are the correspondence of induction principles in reverse mathematics. Okay, you can find other justifications for this, such as there's examples of Ramsey's theorem, which also justify this choice, but I don't want to go too much into that because we are losing some time here. Let me just use Ramsey's theorem to illustrate one problem that occurs here when we are trying to translate a logical theorem into a Weihrauch problem. So Ramsey's theorem on singletons, it's a very simple principle here. It is for every color. It's usually formulated like that. For all colors and all colorings that have that many colors, there's an infinite homogeneous set. which in this case is easily seen to be kind of equivalent to the Bolzano-Weierstrass property. The problem is when we translate this into a Weihrauch problem, what do we do with this universal quantifier here on the number of colors? So there are two options. Either we take it as an additional input. So we have as an input this number of colors and the corresponding coloring, or we just take it as a promise that our coloring is bounded without any explicit information on the bound. Now, these are two different Weihrauch instances of the same theorem in reverse mathematics, and you can argue which one is the correct one. So this distinction has also been noticed by Dennis Hirschfeld in his book, Slicing the Truth. I think his conclusion was that the former is better. I would tend to say that the latter is better. My way to investigate this or to come to this conclusion is look at the property that we have in the end here. So the property that has to be satisfied doesn't require K to be formulated. So in that sense, K is more like an additional information on your coloring. It has nothing to do with the property as such. And therefore, I would tend to read it in the second version that for every bounded coloring, you have such an infinite homogeneous set. And if you read it in the second version, it is actually easy to see that this version of Ramsey's theorem is once again equivalent to the Bolzano-Weierstrass theorem, and likewise for stable colorings, you get the limit operation on natural numbers, which is to be equivalent to choice on natural numbers. So this is very easy to see. The other version, which has the explicit information on bound, however, is strictly weaker. But if you take the closure under composition, then you are back at a choice on the natural numbers. So under closure of deduction, so to say, it doesn't make any difference whether we give the number of colors as an explanation or not. So a similar problem occurs in a recent result of Davis, Hirschfeld, Hurst, Pardo, Pauli, and Yokoyama. They studied these two tutorial principles where you have a very similar situation on the internet. So either you say that for every color something holds, or you just take this as a promise that the function is bounded. But if you look at the condition that has to be satisfied and the number of colors doesn't go into this explicitly, so I would rather read it as a promise of boundedness. But the authors have studied the other variant, which the explicit information on K, and they found that the first principle is equivalent to L. The second one is equivalent to total choice on the natural numbers star. So these are very interesting. And the authors also showed that ERT is sigma 01 boundedness, whereas ECT is equivalent to sigma 02 boundedness. But would it be conclude that LPO star is a representative of I sigma 01 and TCN star is a representative of I sigma 02? I would say no. I mean, this doesn't diminish the value of this result, but it's a wrong conclusion to say these are representatives of the axiom systems because they are not closed under composition. And if you take the closure under composition of these principles, you are back at Cn prime and Cn, which are our representatives of I sigma 01 and I sigma 02 respectively. One could also study the other version where F is just given with the promise that it's bounded, but as far as I know, nobody has studied that. It's an interesting research question. What are the Weihrauch degrees of these variants of these problems? Okay, now this one is not really in correspondence with reverse mathematics, but I also want to briefly mention the bare category theorem here because it's also equivalent to Cn. Because here we can illustrate another thing that's happening. Namely, we can formulate a version and a contrapositive version of the theory. So the usual version is perhaps this one. For all sequences of closed sets that cover the entire space, there exists an index I so that the corresponding set is somewhere dense. So the interior is not empty. Of course, this only works for complete spaces. So I assume that X complete computable metric space, just think of Cantor space if you wish. Then we can have a contrapositive version. If all these sets in the sequence are nowhere dense, then there must be which is not covered. So I'm taking the contrapositive version of what is written in these brackets. And you can see interesting things about all these versions. The contrapositive version is computable, but it's still useful to know this. And the other version is equivalent to Cn. Now, if we look at theorems and their contrapositive forms, it's important that we know what we are talking about here in case of the promise. So here's a more general version of a theorem and a contrapositive. Now, the promise here, I write it as a universal statement as well. So our input is here. The input satisfies this promise, and the output has to be satisfies this property. Now, if we want to go to the contrapositive form theorem, we really have to know how this promise is phrased. So there is a hidden variable z here in the promise, which is the output of the contrapositive form, and we can only know which z that is if we have an explicit formulation of this promise as a universal statement. And then the contrapositive form can be phrased like this. So the input remains to be the same. The promise is of the previous output condition, and the new output in the contrapositive form is the negation of this universal statement here. So in other words, if we want to formulate a correspondent of a theorem and a correspondent of the contrapositive form, we really need to know the exact logical formulation of our theorem. So in other words, the mapping from T to T contra, that's not an operation on Weihrauch degrees, but you have to simultaneously translate this theorem in this precise version into T. You can only read this off precise logical formulation. So in T contra, they really realize the theory as it stands and its contrapositive form, but you cannot easily go from the Weihrauch degree T to its contrapositive form or vice versa. Now, let's look at Weak-Koenig's lemma, where this distinction can also be made. So we have Weak-Koenig's lemma, which is for all trees that are infinite. This is the promise. There exists an infinite path of the. If we formulate the contrapositive form, it's not enough to know that the promise is that T is infinite, but we have to know how this is phrased exactly. One possibility of phrasing this would be to say, for all possible bounds, finite bounds n, the size of the tree is larger, and if you phrase it like this, then the contrapositive form takes this form. It's well known that the first form is equivalent to choice on Cantor space, and it's easy to see that the contrapositive form is computable. So if you know that your tree has no infinite passes, well, then it must be finite, and you just search for a corresponding bound in order to find it. By the way, just a side remark, you need Markov's principle here to find this bound. This is why in constructive analysis, the contrapositive form would not be meaningless. So they would call it the fan theorem, and it's also interesting. But for us, the contrapositive form is a thing. Now, besides the contrapositive, you could disjunctive form of the theorem where you say for every tree, the tree is either finite or it has an infinite path. And you could ask, how should we interpret this as a Weihrauch degree? But now we are a little bit in a trouble because we already know what to do with the OR in our Weihrauch lattice. As I mentioned, we have two versions of the OR, the classical version and the constructive version. So the classical version is mimicked here by this T plus. So here if the promise of the problem T is satisfied, we produce an answer of T together with some dummy result for Z. We produce an answer for the contrapositive version and a dummy result. But if this is thought to be a useful operation in the Weihrauch lattice, the OR requires this completion, and that's a bit unpleasant here. Of course, we could do it without the completion, exactly like this without completion, but then it would even be worse. So, so this is a little problem here. And if we take the constructive version where we are given an answer, an extra bit 0 and 1, that tells us whether the promise of the theorem or the contrapositive theorem is satisfied, then it makes the problem too difficult because it might be very hard to distinguish between these two cases. So it would be unnatural to look at this constructive disjunction. Here's kind of a meta theorem that tells you some things that you can deduce, and the conclusion is very brief here, perhaps the last item. This works well. The classical disjunctive version T plus works well if the problem T is so closed under completion and idempotent. We want anyway because we order composition. However, it doesn't go so well if we don't have completion up with something that corresponds to the completion of the theorem, and that might be harder than the theorem itself. So the conclusion for Weak-Koenig's lemma is Weak-Koenig's lemma is extremely stable under all sorts of operations. It's closed under composition, parallelization, dagger, and also completion. So here everything works well. So the normal version of Weak-Koenig's lemma is equivalent to the disjunctive version. If we take the classical disjunction, the contrapositive version is much weaker, it's computable, and the constructive disjunction is too hard. It's harder than WKL. Okay, now let's briefly look at the situation of arithmetic transfinite recursion. Here I want to mention an example that was studied by Ishihara, Marcone, and Pauli. There are many other people who have looked at equivalence of ATR naught, but their result is on the perfect tree theorem, which is very similar to Weak-Koenig's lemma. Namely, in this case, we are asking that our tree, I mean, this is a tree in bare space now. If the tree is non-countable, then there exists a perfect subtree of our tree. So its logical form is very similar to Weak-Koenig's lemma, except that here, instead of infinite, we have non-countable. And instead of finding a path, we want to find a perfect subtree. Once again, we have exactly what we mean by non-countable. And one way to interpret this would be to say, okay, we just want to have a sequence which enumerates the infinite passes of the tree. This works well except for the empty set. So you have to make some technical additions here to cover the empty set, but otherwise the idea is this one. What Takayuki, Alberto, and Arno proved is that the perfect tree theorem is equivalent to choice on bare space, and the contrapositive version is equivalent to unique choice on bare space. So we have a very similar situation here. So the analogy is that Weak-Koenig's lemma versus the contrapositive form is equivalent to choice on counter space or unique choice on counter space, which happens to be computable. And on the perfect tree theorem side, the theorem versus the contrapositive form is equivalent to choice and unique choice on bare space, respectively. But now, following my thesis and my initial assumptions, it's legitimate to say that the harder of these two versions is the real correspondent of ATR naught. So PTT is known to be equivalent to ATR naught, and in reverse mathematics, the contrapositive form is also equivalent to ATR naught. But this is just because classical logic is available. And if we want to stay in the picture that our lower cone is equivalent to the theory of the theorem, then we have to take the stronger of these two, and that's on bare space. So from my perspective, this result shows that choice on bare space is the true correspondent of ATR naught in the Weihrauch lattice. I don't have enough time to tell you all this, but let me make a brief statement on other theorems that have, or other Weihrauch degrees that have been considered as correspondence. For instance, the totalization of choice on bare space has also been discussed as a version of ATR naught. But if you use that twice, you can already compute the well-foundedness problem. So it rather seems to move you in the vicinity of pi1 comprehension. And also the disjunctive versions, PTT plus and PTT infimum, they are too strong. And this is not a defect of the perfect tree theorem, but I would say it's a defect of the Weihrauch lattice. So it's because the Weihrauch lattice is just not well suited for handling disjunctions. We cannot model disjunctions appropriately. So when we classify disjunctive versions of theorems, we have to have that in mind, that there is no proper version of a disjunction here for that purpose. Okay, now the same three authors also proved that UCN is Weihrauch equivalent to delta 1,1 comprehension. And I think this is correspondent unique choice on bare space. So in Simpson's books, you can also find this analogy that WKL behaves to RCA naught like ATR naught to delta 1,1 comprehension. And so this is a reason to say that this correspondence is really the appropriate one. There are more arguments that you can make to support this thesis, but I don't have enough time to tell you all this. I rather want to come to my conclusion. So I think I have made some points that support my thesis, that you should have closure under composition. And it's not enough that your Weihrauch degree is an interpretation of some theorem which is equivalent to your axiom scheme, but it should be one that is closed under composition. And that makes the cones to be, the Weihrauch cones be closer to the theory of that theorem. But depending on what your formal system allows you to do, you need further closure properties. So if you have countable choice, you need closure under parallelization. If you have classical logic, you need to take the stronger one of the contrapositive form and the original theorem, and so forth. There are other imaginable closure properties that you need to satisfy. So this kind of supports this picture. So I think I've made claims for the induction and the boundedness theorem for WKL, for delta 1-1 comprehension and ATR not. But there's one case which I haven't really talked about because it's perhaps inappropriate to identify ACA not with the compositional closure of limb. Here, the situation is a little bit subtle because it seems that, or it is such that we don't have a single maximal theorem that is equivalent to ACA not and closed under a composition. This is just because ACA not is defined in such a way that this cannot work. For instance, if we have, I mean, we can prove an ACA not that for every n and for every p, the n's jump exists, but the n has to be outside of the statement, so it's not part of the theorem that you prove. So it's kind of an external n. And if you want to move it inside, you already get a stronger version. So this doesn't hold true in ACA not. And if you look into literature, then you will find all sorts of variations of ACA not. You will find ACA prime, which kind of allows you to take finite lists of jumps, ACA not plus that guarantees the existence of the omega jump, and so forth. So in other words, even in reverse mathematics, people don't seem to be always happy with ACA not as it stands, but they look at certain extensions. And our limb diamond is somehow in between such versions, but it's not exactly the correspondent of ACA not as it stands. But this is not a counterexample to my thesis. It just means that my thesis is not applicable in this situation because we don't have a suitable theorem that could serve as the correspondent. Now let me close with a number of open problems or suggestions, what could be studied in this context. So we've seen a lot of such questions during my talk, and this is kind of a summary of these questions. So study the problem of taking a simultaneous closure under composition and parallelization. There's also this question, is there a primitive recursive version of Weihrauch reducibility that would be closer to constructive mathematics without Markov's principle? Find a version of Weihrauch reducibility that is better behaved with respect to disjunctions. So you might not know what full Weihrauch reducibility means, but my conjecture is that it might help. This is something I introduced last year. So it's Weihrauch reducibility with total translations instead of partial ones. Another suggestion is study ECT and ERT with bounded Fs without explicit information on the bound. So would the omega jump really be constructively equivalent to LPO? Is there a theorem whose interpretation is equivalent to limb diamond? That's also an interesting question. And of course, one could find further Weihrauch degrees closed under composition and that correspond to certain axiom systems. So thank you for your attention. So this is the end of my talk, and here are some references for some of the results that I have cited.
Thank you, Vasco. Any questions? Online participants, any questions? Okay, well, thanks again, Vasco.
Many thanks to you as well. So enjoy the rest of your stay there.
Before you go, Vasco, can I just ask, we don't have a consent form from you, so are you okay with the recording of the talk being published on our website?
Yes, sure.
All right, thank you.
Talking about